In this video we're going to retread our OCTC derivation with a slight twist to learn how to calculate the dominant low-frequency pole location. We'll find that pole location using a variant technique called short-circuit time constants. Okay, so I've replicated our midband approximation here, and I've noted that we only really care about our dominant low-frequency pole location for estimating our low-frequency bandwidth. I've also copied over our transfer function. First, we do the same set of convenient transforms we did last time when we were working on OCTC, including the weird choice of making our low-frequency pole zero pairs into canonical form. Next, we note that our high-frequency dynamics term is going to be 1 because each of the tau I times omega minus 3 dBl is going to be small, right? Since omega minus 3 dBl is at low frequency, we know that tau I times omega minus 3 dBh is 1, so this has to be much less than 1 at this low frequency. So we expand our denominator like before, and then we do something tricky. Here we've divided s to the m minus 1 off of both the numerator and the denominator, which leaves us with 1 0 on top, something that looks like a first-order term on the left as the s plus the sum of all the pzi, then plus a bunch of terms that have at least one factor of s in their denominator. Now, because we assume that omega minus 3 dBl is caused by the roll-off at omega minus 3 dBl is caused by a dominant pole, all of these additional terms have to be about 0, because they each contain some pzi over omega minus 3 dBl, and all of the pzi are at even lower frequencies because pz1 is dominant. And that's great. It leaves us with a nice-looking first-order approximation of s over s plus p, 1 0 and 1 pole, where the pole location is given by the sum of all the pzi. Which is fine, but just like open circuit time constants, we don't know what the sum of pi is. However, Circuit Wizards did some analysis that shows the sum of the pi is equal to the sum of the inverse short circuit time constants, where each short circuit time constant is a cap times the Thevenin impedance seen from the cap, assuming that all of the other caps in the circuit are shorted. So this second bullet is reiterating our main point. We can estimate our low-frequency 3 dB corner by adding up the sum of inverse short-circuit time constants. Just like open-circuit time constants, we need to ignore some caps when doing short-circuit time constants. Specifically, we need to ignore high-frequency pole-causing caps because they're all open circuits at the low frequency of omega minus 3 dBl. And finally, short-circuit time constants can be combined with open-circuit time constants to locate higher-order poles if you do some tricky cross-products between them. It's not really worth it in my estimation because the intuition falls off quickly, and the main reason we're doing this bandwidth estimation is so that we get an understanding of our circuits. If you just want to know exactly where every pole is in a transfer function, a computer will tell you that. So, in summary, we can predict our low-frequency dominant pole location as p is equal to the sum of 1 over the short-circuit time constants, where the short-circuit time constants are caps times the Thevenin impedance seen from the cap, assuming all other caps are shorted. But we leave pole-causing caps out of this analysis. We assume they're all open circuits.